All right, so the last solution I did for this problem was time complexity of O square root of n, and I realized that you could actually get a better solution in an O of log of n solution. So here's how to do that. So the idea with the O of square root of n solution was you pretty much take the value, let's call it n, and you'll pretty much check each value from 1 to the square root of n. And remember, we didn't actually use square root of n because the whole idea is we don't know how to find the square root. That's the whole problem of that we're trying to solve. But it doesn't matter. That's what pretty much happened. Like, it doesn't matter if we actually use square root. The idea was to go from 1 to square root of n. So in this case, we check 1 up to 4, right? But we don't actually need to check all those numbers, especially when the number is bigger, when n is larger. We don't want to check each and every number up to the square root of n. That's wasted iterations. We can get it a little bit faster. So to do that, we use a sort of binary search. So if we have 1 up to, let's say, n, the idea is to first check this value, right? The middle value. Let's call it k. And we check, okay, is k squared, right? Or we could write it this way. Is k squared equal to n? Or is it less than? Or is it greater than? Whatever. If it's equal, we found our square, right? We just returned k. If k squared is greater than n, that means n is going to be, or rather the square root of n, is going to be somewhere over here. So we can now, instead of searching from here to here, we can search from k minus 1 to this over here, right? Which in this case would be 1. If k squared is less than n, that means the square root of n is somewhere over here. So we can now search k plus 1 up to n. And that's binary search, right? That's pretty basic. So that's really the intuition here. And similar to the other solution, you have to worry about overflow, but we'll deal with that when we get there. So the idea is we have our left, our rights, right? In a binary search, you have the left value, which is, like, if we're searching in this area, this is our left value, this is our right value, and we'll calculate the middle value, k. All right, so we'll have our left, and we'll start it at 1. We'll have our right, and we'll start it at x, which I called it n, but x is the number of which we're trying to find the square root. And like in the past solution, we'll also have this best factor, right? The best answer we can come up with in case we're working with something that's not a perfect square. So we'll just call it best. We'll just set that to 0. And then, like a normal binary search, we'll do while, as long as the left pointer, if you want to call it that, is less than or equal to the right, as long as left is over here, right is over here. If they cross, obviously, then we're done, right? We've gone too far, we haven't found something, which in this case we will find something. Or rather, we won't, but if we don't find something, we'll still return the best possible value. So as long as we're still searching, we'll have the factor, we'll call it f. And now this part, we're just pretty much finding the middle value, right? We're taking this value and this value and using that to find the middle value. So left plus right minus left. And normally this could look like this. Right minus left. Actually, this has to be parentheses. Divided by 2. And that works for the most part. The problem is, if let's say we have a value like, I don't know exactly what the integer overflow value, it's like 2,470 something, right? So let's just call this int max. Let's just call this im, right? Let's just call it im, right? If right is im, right? If the number we're trying to find the square root of is the integer max, then when we plug this in, when we do this little thing right here, if we were to do it this way, what we do is say im, right? Oh, actually, this would be plus. Excuse me, that was a mistake. We would add them up. We'd say im plus 1, which obviously, because it's integer max plus 1 would overflow, right? And would create integer min. So that'd be a problem for our code. So to solve that, you can use this little trick where instead of doing right plus left divided by 2, you do right minus left minus divided by 2, and then add left to that. And that just keeps you from having an overflow problem. And then we'll create, again, to deal with overflow, we'll use a long instead of an integer and cast this to a long. So again, if you're working with, say the integer overflow is, somewhere around here. It's not exactly integer max, it could be, but it's close, right? Let's just call it integer max, like -3. And if you multiply this by itself, that's obviously going to create overflow because it's pretty much integer max times 2. And if integer max plus 1 is an overflow, then this is definitely an overflow, right? So to deal with that, we just use a long to keep track of the value when you square the current factor. So if that squared factor equals x, then we found our perfect square, and we'll just return f. However, if it's not the right value, if f squared is greater than x, right, which means f squared, let's call this x again. If f squared, which we call this fk, whatever, it doesn't matter. If f squared is greater than x, that means f is somewhere over here, right? And that means the square root of x is somewhere over here. So in that case, we need to, let me clear all this out. In the case where f squared is greater than x, what we'll want to do is readjust our search area to be over here and kind of forget about all of this, right? So in that case, we need to set right, left stays the same, left stays here, but right would need to become, instead of over here, we're going to come here, which would be f minus 1. So in that case, right equals f minus 1. Now this else is pretty much, I like to comment this in just to be clear what it is, if f squared is less than x, and that's the opposite of what we just said. If f squared is less than x means we need to go this way, right? So we'll need to reset the search area to be around here, which would be f minus 1 for the left, and right would say the same. So we'll do that. Left would be f minus 1. And then in the case we don't have a perfect square, this little line here will never be true. F squared will never be exactly x because it's not a perfect square. So we need to be keeping track of the best possible thing we found so far. We do that by doing this. If f squared is less than x, then best, which again, best is just the best factor that we've seen so far, we'll set it to f, right? And what this is doing is we're going through and finding pretty much, let's do an example. Say x or n, whatever you want to call it, is 16. So we have all these values, right? 1, 2, 3, 4, up to 16, right? And what you want to do, we're starting the search here, right? So what we do is say, okay, left plus right. Simply put, we don't have to deal with integer overflow. We don't need to do the more complex little thing. We can just do left plus right. So we'll just do 17, right? Which is pretty much the same result as this right here. Actually, it's the same as this, which we actually need to remove. 17, again, divided by 2, right? And this would be integer division, so this would be 8. So we'd say, okay, 8's our f, this is our f value. And f squared is 64. And we say, okay, is 64 equal to 16? No. Is 64, let's see where we're going, greater than 16? Yes, okay. If it is, we'll say right, we'll move right to be here. Right. And now what we do here is we say, down here, this is where we're doing this, if f squared, which again was 64, if that's less than x, which is 16, it's not, so this is not a good square. We're not going to try to use this, so we'll do a next iteration. So again, 1 plus 7 equals 8, divided by 2 equals 4. This was a bad example. I shouldn't have used a square. I shouldn't have used a perfect square. 17, it's the same example though, same idea. So now 4 is f, right? So f squared equals 16. Now is 16 equal to 17? No. Is 16 greater than 17? No. Is 16 less than 17? Yes. Which means we'll move the left pointer thing to k or f plus 1, right? So we're here. And because this was less, this squared was less than 17, right? We'll remember this. We'll say, okay, just in case anything goes wrong, this was the best thing we found so far. Of course, you know 4 squared is 16, 5 squared is 25, which means the square root of 17 must be 4 point something. Which means in this problem, we're going to truncate that 4 point something and return 4, which is why we're keeping track of best. So at the end of this loop here, we'll just return best. And that's the idea. We're going through and finding the highest number that when you square it is not greater than x in the case of non-perfect squares. And that's the idea. Shit. Huh. This should actually be f plus 1 because the left is getting reoriented to the place just to the right of f. There we go. And see, that's much faster than the O square root of n solution, which makes sense because it's a binary search O of log n. Space is constant.